This conference will now be recorded.
Hello, everybody. Thank you for joining us for the third edition of our Satellite Book Club seminar series. Glad to have all of you joining us today. Hope everybody is staying well out there. Looking forward to introducing our presenter in a moment. As you may have heard, the background on the Satellite Book Club is really to give an opportunity to exchange ideas across the field and also to exchange ideas between the field and the research community when it comes to satellite observations and satellite products. This session is being recorded and we'll have about a 15-minute presentation. After that, there'll be time for questions. Given the number of attendees we have on today, I'd encourage you to go ahead and enter your question in the chat box if at all possible. If you have a nuanced question, we can unmute you at that point for follow-up. Just for any of you out there, particularly in the operational community, we are looking for future presenters. This is, I think, a great opportunity, and I hope you agree to share some ideas for how satellite data can best be applied with your colleagues in NOAA. And to that point, we will have a feedback survey. So if you have any comments on this, we'd like to hear from you how we can make this most effective. If you have any questions for our participants from the field today on how to access satellite data or configure your AWIPS, the Tower S team is available to help with that. And we have Lee Byerly and David Blutis on the line today. They are helping to organize this seminar series, so we're very thankful for that. And we're also very thankful for Brian Mata and Ross Van Til and the rest of the team over in the Office of the Chief Learning Officer, Forecast Decision Training Division. They have the ability to create training materials that may be unavailable. So if you're a science officer out there and you're thinking it'd be great to have some training on satellite, we realize you're very busy, please reach out to them and make them aware of your training related needs. As a side note as well, this is being recorded and will be posted online for those of your colleagues that are unable to make it. So without further ado, I'd like to introduce Chad Gravel. Many of you probably know Chad from the Operations Proving Ground. He was doing great work there, always gives a very polished presentations with some very intriguing insights. He's currently the Techniques Development Meteorologist in the Science and Technology Services Division at Southern Region Headquarters in Fort Worth, Texas. He initiates, plans, coordinates, and oversees the transfer of new and emerging technologies from the research community to the operational forecast and warning environment. So with that, I'll turn it over to Chad. Chad, thanks for being with us today.
Absolutely, thanks, Jordan. And thanks, Lee, David, and everybody who helped put this together. So today, I haven't unfortunately been on the first two satellite book club seminars. I had conflicts, and I haven't been able to go back and look at those yet and watch them. But from the presentations that I saw that were coming, I think this is going to be just a little different take. And I think what you'll end up seeing is this is going to be more like a plea from National Weather Service forecasters and operations to the satellite community. And then maybe we can see how that can go down the road. So without further ado, my presentation is on basically the importance of satellite observations to real-time gridded analyses in NWS forecasts. And when I'm talking about NWS forecasts here, I'm really talking about the national blend of models. And the Weather Service developed what they called the national blend of models back in like 2015, 2014, in that time period. And the goal was to produce or provide a nationally consistent, skillful suite of calibrated forecast guidance so that NWS forecasters could basically use this as a better starting point for their official forecasts. So instead of like loading the the GFS deterministic run or the Euro deterministic run, they would start with this national blend of model suite of products. So that's basically when I talk about the NBM here, this is what I'm talking about. And many, many models go into that. It depends on what element you're looking at. So for example, POP beyond probability of precipitation beyond day 3, there's like 170 inputs into that NBM. So we're talking, 50 European ensemble members, the Canadian ensemble, GEFS, regional models. And you can see how the list can get really, really large really quickly. But the idea is that you can produce a better starting point when you're using the wisdom of the crowds approach than one or two different individual models. And, in the NBM the project really started with the Sandy supplemental funds that were provided to the National Weather Service. So, the idea behind, there's a line in there, statistically post-process model output, and that's hard to explain. So the way that I'm going to do it is with one of the easiest fields to understand, probability of precipitation, and I'm going to try to show you why blending all these models is a better starting point. So if we start with probability of precipitation, it's very simple. It's the probability over a given amount of time. You can define it as an hour or 6 hours or 12 hours, but a probability of any measurable precip. So it doesn't mean if it rains over that 12-hour period 2 inches or 0.01, that's a hit. Okay, so that's what we're talking about when we're talking about probability of precipitation. And I'm going to show a series of graphs here from Hamill et al. 2017 because they really think they illustrate the point really well. So what we're looking at is we're going to look at relay diagrams. The forecast probability is going to be on the x-axis, 0 to 100. Observed relative frequency, so this is basically how often it rained, is going to be on the y-axis. And when you're perfectly reliable with any kind of probabilistic product, you want to be on this one-to-one line that basically stretches from 0 to 100. So for example, if I had a forecast probability of 70%, every time I forecast that 70% of the time it should rain. Again, 2 inches, 4 inches, 1.5 inches, or 0.01 measurable, okay? So the first image I'm going to show is basically just the GEFS NCEP ensemble members, okay? So you use those together, you develop this probability of precipitation, and then you plot it for a long period of time, and you basically plot it on this graph. So when the GEFS in general, remember, so this is based on Hamill et al. 2017, produces a 60% probability of precipitation, it only rains 20% of the time, okay? So this is what we call a wet bias. I'm telling you that there's a 60% chance of rain today, but when I forecast 60%, we're only getting rain 20% of the time. So anytime this red curve is to the right of this one-to-one line, it's basically a wet bias. And you can see just using those ensemble members, raw ensemble members, you basically have a very wet bias, okay? So let's look at the Canadian. So the Canadian ensemble, it does a little better, right? So if we look at that 60% probability, forecast probability, it rains about 35% of the time. So that's a decent amount. The skill is quite a bit better than the raw NCEP guidance, but still it's not great. Now, if we blend those two pieces of guidance, so get about 40, 45 inputs, and just blend the raw guidance, that's what we call a multi-member ensemble, it does a little worse than the Canadian on its own, but it does a little better than the GEFS, which is not surprising, right? You blend them two together, you get something in the middle, okay? So one of the things that the NBM does really well is going to be on the second line, okay? So that what I just showed you was just raw inputs, but in reality, we post-process and we bias correct that guidance. So the idea is if I know over a long-term period that the GEFS, when it forecasts a 60% probability of precip and it only rains 20% of the time, anytime that it forecasts that 60%, I'm going to just put 20% in, right? Because you have this long climatological database that you can just basically, that's what we call bias correcting, okay? And the NBM and the algorithm that goes on, that does this bias correction and weights some of these individual inputs, it's very elaborate and it's just beyond the scope of this presentation. But when you do that by just using that individual grid point, look what happens to that curve. Just using these two ensemble systems, the GEFS and the Canadian, now I'm talking, right? So I'm much closer. So if I look at a forecast probability when it's bias corrected, I'm about 55% of the time it rains. So that's actually pretty decent guidance. It's not perfect, right? Because we want to be along that 1-to-1, but it's pretty good. So instead of taking the one grid point, let's do like a search radius. So let's take a 3x3 area around that grid point, and it does a little better. Still not perfect, right? But so when you do this, when you bias correct it, you're taking some of the noise and you know, the unpredictability around or out of it. So what they do then, one of the next steps is that they quote unquote dress it, okay? So they add noise back into the field and look what happens. So it's just a little more uncertainty because it's, you know, forecasts are uncertain, right? And then if you take that field for letter G and you smooth it, you're pretty darn close. And that's just using the NCEP guidance and the Canadian. So this chart is a very important chart because it really breaks down the methodology that Hamill et al. And others have done to incorporate this type of work into the NBM, okay? Now, the one thing that I haven't talked about yet is what do we use to bias correct it? Well, in the case of probability of precipitation, we're using the stage 4 precip data, okay? And that's basically driven by the river forecast centers. So basically what happens is, you know, you get a probability of precipitation or you get a precipitation field over a certain amount of time. The forecaster goes in and tries to adjust it some, quality controls it, and boom, and that goes out. And that's basically what they use to bias correct it. It's a longer term, and there's a few other things in there, but for our discussion, that's the field that they're using, okay? And that field goes into a gridded analysis called IRMA and RTMA, and I'll talk about those in a second. So just one slide here. So how well does a real NBM do, right? Because I was showing you, you know, basically, you know, from a publication. So over the course of August 2018 through August 2019 across Southern region for a year, you can see the NBM curve is in green, and these are for 96-hour forecasts. So these are 4 days out, and you can see that over all of Southern region, the NBM reliability curve is pretty good, right? And one thing you'll notice is that the official forecast, there's a bit of a dry bias to it. And we won't get into why or why not, you know, that's there. It's really not important for this discussion. But the thing that I really wanted to show you is that in practice, so the data that forecasters are getting that's been bias corrected, right? Because there's biases in these models, clearly. It basically does a good job. It falls pretty close to that 1-to-1 curve. So that's what I wanted to show there. Okay. So let's talk a little more about these gridded analyses. So that there's two that we're really going to talk about. for the most part, I'm going to talk about IRMA, which is the unrestricted mesoscale analysis. But really, these two analyses are very, very similar. And really, the main difference is that IRMA is run 6 hours later to incorporate observations that arrive too late for the real-time analysis. So the real-time analysis is basically you get it within about 80 minutes, I think. So if a 12Z RTMA gridded analysis, you would get it about 1320 or so. At least that's when the Weather Service forecasters get it. But IRMA comes out about 6 hours later, and it incorporates some observations that just maybe they don't come like a polar pass, right? There's polar observations. There could be mesonet observations that don't make it in, or METARs that don't make it into the cutoff for the real-time mesoscale analysis, but they would make it in for IRMA, okay? Let's see. So basically, IRMA is the observation-based truth analysis for the NBM. It's the data set that the NBM is used for bias correction and weighting certain inputs, but it's also used for verification as well. So it's a very, very important data set for these forecasts for this initial starting point. So that's why I'm talking about how important it is for gridded analyses into the NBM, and that's where the satellite data ties in, right? But one of the big issues, in my opinion, is that there's only a few satellite observations that go into these analyses. There's the GOES imager, okay? There's ASCAT wind speeds over water. There's WindSat wind speeds. There's satellite low-level cloud drift winds, and there's satellite altimeter data as well. So there's not a ton of data that goes into these fields. So we'll talk about that more at the end. There was something else I wanted to say, but I think I'll save that. Okay, so let's take a look at a real example. Okay. Oh, sorry, one more thing. So these gridded analyses, they're not all observations, right? There's a background field associated with them. So it's basically a starting point for the analysis. And that background field is a weighted blend of the latest 1 hour 3 kilometer HRRR, and then the most recent 3 kilometer NAMNES forecast downscaled to a 2.5 kilometer grid, basically, the most recent one. And the weight of each forecast depends on how much time has elapsed between the forecast and the analysis. So you can imagine there's certain forecast hours where the NAMNES is weighted a little more, and then there's others, because it's a little older, it's weighted a little less, okay? So that's very important. And one of the things I want to point out is a lot of times when the satellite community and satellite developers and researchers think about their products or their observations getting into the models, they do think, you know, data assimilation, they think about the HRRR, right? Or the NAMNES, or these regional high-res convection allowing model type guidance. And that's clearly super important, because it is the first guess and it's a background field, okay? But there potentially could be a little more application. So we're going to take a look at an example. And one of the examples, the example I'm going to show you, are winds across the Gulf Stream. So this is a 24-hour forecast. It was initialized on the 21st of January from 2020, so just this past January. And it's valid 24 hours later, the next morning. And I'm just going to point out a couple quick things. So here's Florida, and basically what we're looking at is this is the Gulf Stream, and we're really interested in this regime for winds across the Gulf Stream, because this was a pretty dynamic day. Strong cold front move across the area. Just you know, just an opportunity for maybe the models potentially not to do as well as they could potentially. Okay, so this is the Gulf Stream. So in this green, we have basically winds 30 to 35 knots. In this lighter green here, we have winds maybe 25 to 30 knots or so. And anything in this light blue area basically from Miami to the south across this part of the Gulf Stream, is basically the low 20s. So 22, 23 knots, give or take. But you just get the general idea, lighter winds down here in the Gulf Stream, stronger winds to the north, okay? So what actually happened that day? So here's an ASCAT pass, okay? And I want to really focus your attention on the red barbs, okay? And really it's the red, and then there's a pocket of orange here. But for the most part, these red barbs are barbs that are upper 20 knots to maybe low 30 knots in that ballpark, okay? And you can see there's spots to the north. So in this area where the NBM forecast was pretty good, but what do you notice? Look down in the Gulf Stream here where you have this really nice ribbon of upper 20 to low 30 knot sustained. Okay, so these are just 10-meter winds in this area, and look where they're co-located within the forecast, right? So it's lower NBM forecast here. So we're talking like maybe 5, 6, 7 knots lower. And, you know, some of you may be thinking, Chad, well, that's not really a big deal. But, you know, forecasters have noted that there's this NBM systematic low bias of around 5 knots, sometimes more, in certain regimes. Especially this one where you had really strong lapse rates. The Gulf Stream is really warm, right? So you're taking that surface condition, right? And you have pretty cold air aloft. It sets the recipe for pretty strong sustained winds. But this bias, this low bias in the NBM forecast can really be problematic, especially when you're talking about the difference between a high-end small craft advisory, which is in the 30 to 35 knot range, which is kind of close to what was observed by ASCAT, and the gale warning, which would be 34 knots and above, right? So this is why this is important. So even though it doesn't seem important, when you kind of dig in the details and you put yourself into the Weather Service forecaster who's trying to make a decision between a small craft advisory and a gale warning, it could be important, okay? All right, so let's dig a little deeper. So here in the bigger image is that NBM forecast, but on the right, here on the top, here's Irma, valid at this time, 12Z on that Wednesday, and here's RTMA, and they look remarkably similar, don't they? And look what Irma has as well. And it has a really aerial low. And honestly, when you look at the NBM forecast and you look at Irma and RTMA, they look pretty darn close for the most part. You know, all things considered, the spatial continuity is there. You have stronger winds to the north, weaker to the south, right? But if you remember the ASCAT pass, those winds were much higher. They were in the upper 20 knots sustained to low 30 knots. And let me go back one time. And digging a little deeper and asking the question, that ASCAT pass never made it into Irma and RTMA, okay? And that's a problem. So why is that? And you know, and I don't have that answer, but if we have really good quality satellite obs and they're not making it into RTMA and Irma for some reason, regardless of what that reason is, it could be quality control, it could be timeliness, it could be whatever, that's a target of opportunity for the satellite community to improve these gridded analyses on the right, okay? Now, one thing that's gonna improve these gridded analyses is the HER background field, okay? So here's the HER background field that was used that day. And what you'll notice looks pretty similar to Irma RTMA. Color scales are different, but we're talking 20, 25 knots in this area where ASCAT had 30 and sometimes 30, 35 knots, right? Now look at the new version of the HER that should be implemented at the end of June, last week of June, early July. So we're about a month out. Okay, now we're talking, right? And now you can see that this orange area here, we're looking at winds 25 to 30 knots, and even this darker orange area just off the coast of Miami, 30, 35 knots. This looks much closer to the ASCAT pass, right? Even though it wasn't included in this background field. Well, the reason is the HER development team has implemented a new boundary layer conditions for basically wind speed over water. And they've worked with the research community, and they're implementing this. And you can see, I know this is one case, but this does a good job. Now, one of the things is we still don't have those satellite observations in. So maybe that could even improve this first guess or this HER analysis or 1 hour forecast even more. Okay, so why does all this matter, right? If the IRMA analysis is not representative, so in this case, too low, of the Gulf Stream winds, then the NBM input bias correction, so all those members, all those inputs that go in the NBM for that wind field, the bias correction will insert IRMA bias, too low, into those forecasts. So you're starting off you don't even have a chance, basically, right? So that first guess, now, and one of the problems is, well, you could say, well, Chad, if it's a systematic bias, the forecaster should be able to adjust 5 degrees up. Well, it's not that easy, right? In this regime, it is a systematic bias, maybe. So sure, that's a target of opportunity for the forecaster. They see this cold front coming. They need to up maybe those NBM first guess winds 5-7 knots. But other times it may be representative. You might only be off a knot or two under certain regimes. And that's one of the big challenges. And that's why we really need the best starting point that we can get. That's why the IRMA RTMA analysis is so important. And that's why satellite observations into those analyses is critical. And so for example, if the model wind forecast is 28 knots, so that would, let's just assume that's a good forecast, but a forecast of 28 knots is over forecast when compared against the IRMA, then the NBM input will be reduced. So it really goes back to making, one of the strengths of the NBM is the bias correction, because all these models, like I showed in the POP example, they're very, they have their biases on their own. It depends on the physics and the initial conditions. There's just so many things. The atmosphere is chaotic and it's hard to predict. So that's why we use these observations and these climatological data sets to bias correct them, make even better forecasts. So here are some NBM core elements. It's not all of them, but these are like your targets. So if the satellite developers are out there, so whoever works on the temperature in the dew point fields, we need to get them involved with the IRMA RTMA folks. There's precipitation, there's wind speed and direction, like I showed. There's wind gusts, relative humidity, there's aviation fields, ceiling and visibility, and then there's weather type as well. So, and that's that's the current state. But what about going forward? RTMA and IRMA are going to undergo in the next couple of years a huge upgrade. And it's basically a 3-dimensional RTMA and IRMA, and they're already prototyping some of this guidance. So in 2013, the current 2-day analyses will evolve to a fully I have 3 in there twice, 3-dimensional analyses with sub-hourly updates. So we're talking updates every 15 minutes potentially. Right now, we only get the IRMA and RTMA every hour. So if you think about it, not only is this going to be great for the NBM, but think about mesoanalysis and real-time forecasting, real-time forecasting and warnings and things like that. And but by going to this 3D IRMA RTMA, those surface fields are going to be so much better, because now that you're going to be able to produce these using a full column representation of these fields, right? And then, the seed that I'm going to plant on this slide is how important do you think a hyperspectral environmental suite of instruments will be for these analysis on the next generation of GOES? You got to think that this is going to be so important for these analyses, because we don't have RAVs every grid point, right? But if we could potentially get really high quality sounding full column representation of the atmosphere using a hyperspectral suite of products, right? So that's my plug there for the hyperspectral challenge. So this is the challenge. It's really getting the satellite developers in contact and communicating and trying to get their products, not pushing their products, but working with these people, working with these developers, you know, really in an R2O process, right? If you think about it, it's really R2R, but it's really R2R2O. So I would challenge you to reach out to these people, into the IRMA and the RTMA developers, because not only is it going to make better gridded analyses, but it's going to make better National Weather Service forecasters, especially since we're starting in certain days 3 and beyond with the national blend of models as a starting point. So with that, I have no idea how much time I took. Wow, I took 30 minutes, so that's not good, Jordan. But I have a few minutes for questions. So I hope it was insightful, and I hope that, you know, people can think, you know, just a different approach to this problem.
Chad, thank you. Your passion certainly carried us through the whole half hour there. Maybe if I could just ask one question, everybody else might have to get in touch with you via email, or we'll be sure to forward them. But, you know, knowing this problem with some of the biases and recognizing that, what's a practical step that a forecaster can take if they recognize this is happening? How can they adjust their forecast to make sure that the NBM is not biased because of the observations?
Yeah, and that's a great question, and it's a challenge right now. And you know, another example is we get these in the Southern Plains, Oklahoma, Texas, etc. We get these shallow cold air outbreaks, and the forecasters can see them coming miles away, right? But because the high resolution inputs are only a part of the game, even, you know, a couple days out, and most of it's more coarse global models, you're going to have a really warm bias on those temperatures. So what we're trying to get forecasters to do now, at least with that element, is take a look at the suite of inputs, or the PDF. So if they see that target of opportunity coming, and they know that the NBM has a 42 for a high, but in reality we might be closer to freezing, then maybe take that 10th percentile temperature, which is 34 in the NBM suite, and start there as a starting point, because you've used pattern recognition, you know, you've used all your meteorological knowledge to identify where the NBM might be too warm there, and maybe use that as a starting point. But it's a challenge right now, and it's something that we're working on, you know, pretty hard at the regional and national level.
Okay, Chad, well, we'll have to leave it there. If anybody else in the audience has questions for Chad, that was a really intriguing presentation.
Feel free to email me.
Yeah, please feel free to get in touch with them, or Lee Byerly and David Blutis can also put you in touch if there's a question there. So thanks so much. We do have a session lined up for next week. We will be back at the noon Eastern time. Scott Rulowski from NESDA Star is going to be talking about some applications for the geostationary lightning mappers on GOES. So please, I hope you were intrigued by this presentation, and tune in again next week. More information is going to follow up in an email from the TowerS team. So with that, we'll close out. Hope everybody stays well. On behalf of the National Weather Service Office of Observations, take care, and we'll see you next week.
Thanks, everyone.